For Lab 1, I observed an object moving horizontally at a constant velocity in the positive x direction. In order to analyze this movement, I used the concept of Newton's second law. Newton's second law related to velocity states that the final velocity equals the initial velocity plus the net force acting on the system divided by the mass of the system, multiplied by the amount of time the force is active. However, in this experiment, we will assume the net force on the system is zero, eliminating the second term in the above equation and making the final velocity equal to the initial velocity, which is equal to our velocity for the entire experiment. Later, when making a model for our experiment, we will use the form of Newton's second law that tells us about position, as shown on the screen. This equation tells us that the final position equals the initial position plus the velocity times the time that the object is moving. For my object, I chose a car coming off the interstate onto an on-ramp. Here, the car is our system and everything else is our surroundings. Next, I tracked my video using the tracker software. Notice in the bottom right corner the data points collected. These will be used later in the process. Also notice in the top right corner the graph of the position tracked versus time. Now that I have my points tracked, I can use the two initial points to estimate my velocity. I do this by using the formula for average velocity, delta r, the position, over delta t, the time. This comes out to be 13.091 meters per second in the positive x direction. I then apply Newton's second law to evaluate velocity for the entire experiment. However, as said before, the net force is assumed to be zero. Therefore, the final velocity is equal to the initial velocity, which is equal to the velocity that we will use for the entire experiment. Next, using the concepts we've previously discussed and the data collected, I can make a model describing the motion. Here is part of the original and modified code. First, I changed the ball's mass from 1 kilogram to the approximate mass of a car, which I estimated to be 1225 kilograms. After that, I changed the initial position vector to the initial position that I tracked in Tracker. After that, I changed the initial vector for velocity to the vector velocity that we calculated earlier in the video. I then changed the part of the code that calculates the velocity and position of the ball using iterations to better match my observations. I first changed the time to match the time I recorded the car moving, from 2 seconds to 0.633 seconds. Next, I changed the fnet vector to 111 from 111 to 000 because we assume that the fnet is 0. I also changed the original equation to find the ball's velocity to Newton's equation, which, as before, states the final velocity equals the initial velocity plus the net force over the mass times delta t. After that, I changed the position vector to the equation for position, which is shown on the screen. Finally, I run the code and see a model of my object as well as a graph of its position versus time. The model is in the top left-hand corner and the graph is in the bottom right-hand corner. After I got the data from the Tracker and VPython model, I plotted the position versus time data from both. Here you can see the data from the experiment is shown by blue dots and the data from the model is a red line. The model is extremely accurate at the beginning of the graph. However, as time progresses, it becomes less and less accurate. This could be because the car was not tracked correctly in Tracker or because I didn't pick the best points to take the average velocity. However, the most likely reason is that the net force of the car is not actually zero. It is coming off the interstate to a red light, so it is more than likely slowing down. This answers the question, do all the forces actually add to zero? In fact, the forces do not add to zero on this system. There are forces from the surroundings acting against the system, such as friction from the road, air resistance, the brakes of the car, and even gravity, since the road is at a slightly positive angle. Now, what would happen if the x and y axes in Tracker would have been switched? As you can see in the top right-hand corner, the y versus t graph, the bottom graph, now looks like the original x versus t graph. The now x versus t graph, originally y versus t, should be a straight horizontal line at 0, but due to errors in tracking the system, it looks jagged, like our original y versus t graph would have looked.